Is this visible?
Yes, sir.
You see the Ramanujan's Lost Notebook in 5 volumes, Afterthoughts?
Yes, sir. Yes, sir. I see it, sir.
Okay, good.
Good morning, sir. Good morning.
Good morning. Good evening to you.
Thank you, sir. Thanks.
Rangnath, Dr. Rangnath? Dr. Rangnath?
Yes,
Dr.
sir.
Rangnath?
Yes, yes, sir.
This is Rajiv on this end.
Yes, yes.
I'm with Dr. Bharat here.
Okay.
We request you to go live. Like it takes a delay, so it's a good idea to go live, I believe, on YouTube.
Yes, sir. It is already in live, sir.
Not yet. We have been checking the transmission here. Hope you have gone live, right? You have already gone live.
Yes, sir. Yes, sir.
Okay, that's perfect. Then it will start exactly at 6. Well done. So is it telling streaming there in YouTube? Just kindly confirm.
Yes, sir. It is custom live streaming service provider.
Perfect. Yeah. Thank you.
내가 Good morning, Professor Andrews.
Good morning. Good to see you.
Yeah, nice seeing you too. We look forward to the talk. Yeah. The title sounds very interesting.
I hope so.
We will start at exactly 6:15, sir.
Okay.
Shall we start, sir?
Sure.
So good evening to one and all, and good morning to Professor George Andrews, sir. So it's
Good
my
evening
pleasure
to
to
you.
welcome all the participants of ICND 2021 to session number 8 of this conference. So in this session, two world foremost mathematicians in the work of Srinivas Ramanujan, namely Professor George E. Andrews and Professor Bruce C. Berndt, are speaking on Ramanujan's notebooks and the last notebook. Now I welcome Professor Atul Dixit to chair this session. Dr. Atul Dixit, currently Associate Professor of Mathematics at IIT Gandhinagar. He got his doctoral degree from the University of Illinois, USA, under the guidance of Professor Bruce C. Berndt. He is the first Indian mathematician to win the prestigious Gabor Sejo Prize for the year 2021 for impressive scientific work in solving problems related to number theory using special functions, in particularly related to the work of Ramanujan. He was recently elected as a member of the Indian National Young Academy of Science for 5 years from 2021 to 2025. Once again, I welcome Professor Atul Dixit to chair this session. Over to you, sir.
Thank you, Professor Ranganath. Good evening, everyone. So in this session 8 of the 4th day of the conference, we have two very eminent mathematicians, as Ranganath already said, who are going to give public lectures based on Ramanujan and his mathematics. So we will begin this first talk with Professor George Andrews. George Andrews is the Evan Pugh Professor of Mathematics at Penn State University. He is one of the world's leading authorities on Ramanujan and his work, and world's foremost authority in the theory of partitions. Professor Andrews discovered Ramanujan's lost notebook in 1976 at Trinity College, Cambridge. And we all know how influential Ramanujan's lost notebook has been in the work of various mathematicians. So without further ado, I will invite Professor Andrews to enlighten us on the afterthoughts of Ramanujan's lost notebook in 5 volumes. Over to you, Professor Andrews.
Thank you very much, Atul. Thank you, Ranganatha. Thank you, everyone, for attending this evening. Perhaps there are some attending this morning. At least I am attending this morning. In any event, what I hope to do today is to look back on the decades that I have collaborated with Professor Bruce Berndt on bringing out the 5 volumes that prove the formulas that appear in Ramanujan's lost notebook. So this is, of course, the man we are celebrating, and that's celebrated in National Mathematics Day. He is, as all of you know, a hero in India. Stamps have been issued in his honor. This is one of the stamps. Cambridge University, where he collaborated with G.H. Hardy, find him a useful item for promoting Cambridge Center for Analysis. And you see here a variety of people of whom Cambridge is most proud. Alan Turing on the far right, Ramanujan standing with Jeans in the center, and Isaac Newton just to the left of Ramanujan. So Ramanujan is revered throughout the world. Ramanujan does not seem to have had any definite occupation until 1912, writes G.H. Hardy. In 1909, he married, and it became necessary for him to have some regular employment. But he had great difficulty in finding any because of his unfortunate college career. About 1910, he began to find more influential friends, Ramaswamy Iyer and his 2 biographers, but all their efforts to find a tolerable position failed. In 1912, he became a clerk in the office of the Port Trust of Madras at a salary of about £30 a year. He was then nearly 25. So Ramanujan's life was not one that was easy. However, he wrote to various English mathematicians. 2 of them basically ignored him or thought he was just a mathematical crank. But this letter to G.H. Hardy was most successful in getting him, getting the attention of a famous mathematician. Dear sir, I beg to introduce myself to you as a clerk in the accounts department of the Port Trust office of Madras. Salary of only £20 per annum. I'm now about 23 years of age. I've had no university education, but I've undergone the ordinary school course. After leaving school, I've been employing the spare time at my disposal to work at mathematics. I have not trodden through the conventional regular course, which is followed in the university course, but I'm striking out a new path for myself. I've made a special investigation of divergent series in general, and the results I get are termed by the local mathematicians as startling. I would request you to go through the enclosed papers. Being poor, if you are convinced that there's anything of value, I would like to have my theorems published. I've not given the actual investigations nor the expressions that I get, but I've indicated the lines on which I proceed. Being inexperienced, I would very highly value any advice you give me. Requesting to be excused for the trouble I give you, I remain, dear sir, yours truly, S. Ramanujan. And in this letter were fabulous formulas. I cite two that struck Hardy most impressively. And he writes about them. I had never seen anything in the least like them before. A single look at them is enough to show they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. Finally, the writer must be completely honest, because great mathematicians are commoner than thieves or humbugs of such incredible skill. So, Hardy brought Ramanujan to England. They collaborated on things that set the course of much of number theory for much of the 20th century and into the 21st century. After being there for several years, Ramanujan contracted an illness of which there's great controversy as to what it really was. But in any event, he became very ill and spent at least a year in nursing homes in England. In 1919, it was decided that perhaps if he returned to India, his health would improve. And so he sailed back to India in 1919. His health worsened and he died in April of 1920. While he was there, he wrote only one letter to G.H. Hardy, which is dated in early 1920. And in it, he described Mach theta functions. And what you see on the screen here is a reproduction of part of this letter to Hardy, in which he is describing these Mach theta functions and telling Hardy about their properties. This is the second page of his letter. The first page is devoted to what he called functions of the third order. And then he goes on to Mach theta functions of fifth order. There are further Mach theta functions of fifth order, which he lists on this page. Finally, at the bottom of the page, he lists Mach theta functions of seventh order. And he says these are not related to each other. Ever yours sincerely, S. Ramanujan. So the question was, since he was obviously doing work because of the contents of this letter, one was interested in what the actual background was in coming up with these formulas that he's written on these pages. And as was mentioned in the introduction, in 1976, I was in Cambridge University looking at papers from the estate of G.N. Watson, and in the collection of papers, there was this manuscript from Ramanujan with formulas related to the Mach theta functions. Although there are very few words in the manuscript, in particular, the phrase Mach theta functions does not appear there. But since I had written my PhD thesis on the Mach theta functions, I recognized them immediately, which of course then tied down the fact that the manuscript I was looking at was the background to this famous letter that Ramanujan had sent Hardy. So I tried to explore what the history, how they got there. And J.M. Whittaker, the son of Whittaker and Watson fame, wrote the following in a letter to me. When the Royal Society asked me to write J.N. Watson's obituary memoir, I wrote to his widow to ask if I could examine his papers. She kindly invited me to lunch, and afterwards his son took me upstairs to see them. They covered the floor of a fair-sized room to a depth of about a foot, all jumbled together, and were to be incinerated in a few days. One could make lucky dips, and as Watson never threw anything away, the result might be a sheet of mathematics, but more probably a receipted bill or a draft of his income tax for 1923. By an extraordinary stroke of luck, one of my dips brought up the Ramanujan material, which Hardy must have passed on to him when he proposed to edit the earlier notebooks. So there is various, Professor Berndt and I have made various guesses about how the lost notebook passed from Ramanujan's hands in 1920, finally into this box in the Trinity College Library. But in any event, fortunately, it was there and was found. Here is a page from the lost notebook. And one of the things to note in talking about this work is that it was, so to speak, mathematics way ahead of its time. In the early 1940s, Freeman Dyson made conjectures about the Ramanujan Congruences, which were known throughout the 20th century because Ramanujan published on them when he was in Cambridge. Dyson made very interesting combinatorial conjectures about these congruences, and Atkin and Swinnerton and Dyer were able to prove Dyson's conjectures in the early 1950s. The main engine that they had for their proof, the main theorem that makes their proof work, sits here on this page in Ramanujan's lost notebook. It is the identity for little f of q to the 1/5 that you see in the fourth line of this page. And so something that was a major source of interest and conjecture and effort was already sitting in the lost notebook known to Ramanujan in 1920. Again, one sees numerous pages on the lost notebook which look like this, very neatly written, formula after formula after formula. There are no proofs in the lost notebook. That is part of the reason why Bruce Berndt and I spent 5 large volumes published by Springer to actually approve these formulas. This page I've always found especially interesting because if you look at the first 6 equations, or first 5 equations, you will see that on the right-hand side, there are instances of the triangular number series. In other words, the exponents on Q on the right-hand side of each equation are either, as in the first line, the triangular numbers themselves, or multiples of the triangular numbers, excuse me, such as twice the triangular numbers in the second line, 3 times it in the third line, 4 times it in the fourth line, and 6 times it in the 5th line. On the other hand, the left-hand sides give no clue of the fact that as you pass from line to line, you're really replacing Q by a higher power of Q. So this is one of these great surprises that Ramanujan lists here without any proof at all. And I would only say of these 5 formulas that when I started working on them, I could do the first one in maybe 10 minutes. I could do the second and fourth in a half an hour, and the third and fifth required several months to be proved. Many of the pages of the lost notebook look like this. So this is a particularly troublesome page to understand, primarily because the mathematician's old friend, the equal sign, does not appear anywhere on this page. And so these are the sorts of calculations that Ramanujan was doing in order to produce lovely, neat pages that look like that. Again and again, you see in here, we obviously have some sort of long calculation, but again, there is no assertion of what what is being involved. Ramanujan is gaining some of his insights and his ideas from this, and unfortunately not telling us what indeed is going on. Actually, I would point out that most of the pages of the Lost Notebook have no words on them at all. Even this page, one sees about the fourth line sees an n equals 1 or 2, or being the only word on this page. And this makes it such that if you don't know what's happening, if you didn't recognize that the Mach theta functions appear, say, at the bottom of this page, you would have no idea what was going on. And presumably, most people not having paid attention to the Mach theta functions, as I said, having fortunately written my PhD thesis on them, I was in this almost unique position in 1976 to recognize what a treasure this volume actually is. So I want to give you some flavor of the sorts of surprises that exist in the Lost Notebook, and to give you an idea of how the Ramanujan's discoveries lead to things that have flourished throughout the 20th century and now into the 21st century. So here are three identities that look very much like the series that you saw on the earlier pages. The denominators are these sort of rising Q products. Of course, in the one at the bottom, there are plus signs, where in the other two, there are minus signs. Some rise just according to the natural numbers, 1, 2, 3, et cetera, up to n. Others, the second line, excuse me, rises according to the odd numbers. The numerator in each case has a -1 to the n and q to some quadratic expression, n squared in the middle one and the n choose 2 in the other two instances. The surprise comes from determining what these series are equal to. The first series is equal to 1. Second series is equal to 2. And the third series is equal to 3. So I've often made the joke, this is as simple as 1, 2, 3. Of course, I've cheated a little bit to make this work by adding 1 to each of the series on the left-hand side. I could have left the ones out, but then there is the humor would be lost if I said it's as simple as 0, 1, 2. I've chosen these formulas because they look very much like and are related to formulas in the Lost Notebook, but they allow me to provide in this talk at least one proof of the formulas of this type. So they all follow from the formula that you see at the top of the screen here. In other words, I've introduced a second parameter. If you set t equal -1, you get the thing at the bottom of the screen. If you multiply by 1 plus t and set t equal to -1, you get the first formula, and you have to replace q by q squared and t then by q to get the formula on the second line. So, but how do you prove this? This has a truly lovely proof. So what you do is you split off the first term, the n equals 0 term. And the n equals 0 term is only 1 over 1 plus t. And then now you have the rest of the sum running from 1 to infinity. You now shift the index of summation from 1 to 0 and replace n by n plus 1. And lo and behold, you see that what happens is that you get f of t with t replaced by t times q. And so you have this functional equation, which is an actually defining functional equation if you treat q as fixed and t as a function of, as a complex variable. Then this functional equation uniquely defines this, provided that you require that f of 0 equal to 1. But The constant function 1 satisfies the same defining equation, and therefore f of t equals 1, and that proves this theorem. So I must admit, given the fact that Bruce and I have slogged through 5 volumes, that not all the proofs are as simple or as lovely as this one. At least this one is ideally made for a talk that is going on in the evening for most of you. So, one of the things that appears often in the Lost Notebook are formulas related to the Rogers-Ramanujan identities. And so this is the first Rogers-Ramanujan identity. You see the same sort of series on the left-hand side of this equation where you have the rising q factorials, 1 minus q, 1 minus q squared, 1 minus q cubed. The exponents on q are the perfect squares. So Ramanujan often wrote series like this with a plus sign and 3 dots at the end, assuming that you would see the pattern. And so obviously the next term will be q to the 16th, the square of 4, divided by 1 minus q squared, 1 minus q cubed, 1 minus q to the 4th. On the right-hand side, you have this infinite product where the exponents are basically all the numbers whose last digit is 1, 4, 6, or 9, or if you wish to say it in more succinct terms, the exponents are the numbers congruent to 1 and 4 modulo 5. The second Rogers-Ramanujan identity, both this previous function and this function appear extensively in the Lost Notebook. This is just a slight change of everything. The denominators in the series are exactly the same, but the exponents are what are called the pronic numbers, or the numbers that form n times n plus 1. So a product of 2 consecutive integers. 2 is 1 times 2, 6 is 2 times 3, 12 is 3 times 4. Obviously, the next term will be q to the 4 times 5, or q to the 20th, divided by 1 minus q squared, 1 minus q cubed, 1 minus q to the 4th. On the right-hand side, I see I have a missing equals sign, so please try to imagine an equals sign between these two expressions. The exponents now are the numbers whose last digit is 2, 3, 7, or 8, or if you prefer, the numbers congruent to 2 or 3 modulo 5. These theorems, both the first and second, were not interpreted by Ramanujan as something involved with partitions, but P.A. McMahon and Isai Schur both gave partition theoretic interpretations. So a partition of an integer is a sum of positive integers, and order is not to be taken into account. So what we do is to have a canonical order, namely the largest part is first, the next largest second, etc. And so I've listed here the 5 partitions of 4, so that P of 4 equals 5. And Euler is the person who really originated the study of partitions and determined generating functions for several classes of partitions. In particular, one of the things Euler proved is that the number of partitions of n into distinct parts equals the number of partitions of n into odd parts. So I want to give you an example so you can see that the partitions involved are quite different. If I take n equal 10, here are all the partitions of 10 into distinct parts, and there are 4, 5, 6, 7, 8, 9, 10 such partitions. And on the other hand, if I partition 10, please forgive my cuckoo clock. If you partition 10 into odd parts, here are the partitions into odd parts. And what Euler proved was that indeed that you will always get the same number of partitions, whether you look at partitions with distinct parts or partitions with odd parts. I should add that his proof, my belief is that he came upon this primarily because he was also studying infinite products and infinite series and really developing what all of us see as advanced calculus these days, and found that infinite products could be used very effectively to study theorems like this. And this theorem, in a sense, fell into his lap because of an easy proof involving the generating functions, which are infinite products. Also, of course, I must mention L.J. Rogers, who it was the first name in what Hardy dubbed the Rogers-Ramanujan identities, because Rogers actually discovered these identities 20 years before Ramanujan discovered them, but he wrote them in a very obscure paper with the title Second Memoir on the Expansion of Certain Infinite Products. And most people had not been able to drag themselves through the first memoir on the expansion of certain infinite products, and absolute mathematical gems lay undiscovered until Ramanujan, browsing through old issues of the Proceedings of the London Math Society, unearthed Rogers' magnificent achievement, and subsequently Hardy arranged for a joint publication of Rogers and Ramanujan, giving new proofs of these identities. McMahon, as I mentioned, published interpretations of these theorems in terms of partitions. So the first Rogers-Ramanujan identity as a partition theorem is the number of partitions of n into parts that are differ by at least 2 equals the number of partitions of n into parts congruent to 1 or 4 mod 5. So here's an example. You now require not only that the parts be different, but they differ by at least 2. And here you have the 7 partitions of 11 where the parts differ by at least 2. And on the other hand, you have the partitions into parts congruent to 1 or 4 mod 5. Notice that there are very little overlap. Indeed, the only partitions that are in both columns are 11 itself and 6, 4, 1. So this part of the talk, I want to emphasize, so to speak, a major direction in research that has flowed from the efforts of Ramanujan. And so I will start out with the sort of standard thing that most mathematicians do, is that anytime they see 2 points, they try to draw a straight line between them, or they linearly project. So Euler's theorem can be interpreted as follows: the number of partitions of n with difference at least 1 between parts equals number of partitions into odd parts, but odd numbers are also the numbers congruent to 1 and 3 mod 4. Rogers-Ramanujan identities require difference at least 2 and the parts congruent to 1 or 4 modulo 5. So anyone seeing these first 2 lines here would think clearly that, what if I try a difference at least 3? How about, and now here I've made it an unforgivable error, so you'll forgive me. I want parts congruent to 1 or 5 mod 6, because if this is going to be a linear progression, the modulos 4, 5, and 6, and 3 and 4, obviously you want parts congruent to 1 or 5 mod 6. So please forgive me for that. So one starts out to see if this is true. And so one of the wonderful things today in the study of the theory of partitions is that we have available to us something that was not available to Rogers, not available to Ramanujan, not available to McMahon, which is all these wonderful computer algebra packages. So while one may well be not a 10th or 100th as smart as Ramanujan was. You have these magnificent machines to sort of help level the playing field just a little bit. But even in 1919, one could start checking this theorem out. And as you'll see on this page, the theorem difference greater than or equal to 3, and now I do have 1 or 5 mod 6. You look at 1, there's only one partition. 2, there's only 1. 3, there's only 1. 4, there's only 1. And if we look at 1 or 5 mod 6, until you get to 5, you only have 1s to use as sum ends. So you get the same number. At 5, there are 2 partitions where the difference is at least 3, 5 and 4 plus 1, and that matches up with the 5 and the 5 1s on the right-hand side. At 6, there are only 2 examples again. At 7, there are 3, and that works fine. At 8, there are still 3, and on the right-hand side, 7 is, of course, 1 mod 6. So you can use 7, 7 plus 1, 5 plus 3 1s, and 8 1s. So obviously, if you were the first person to write out this page, your heartbeat is now rather increasing substantially in that it looks like this theorem might be true. But unfortunately, 9 looms. And here are the 4 partitions of 9, where the difference between parts is at least 3. But the only numbers available to you to use in the second column are 7, 5, and 1. And no matter how you work it, there are only 3 such partitions. So what's the answer to this? Isai Schur persevered. He found empirically that the theorem could be rescued if the partitions with parts 3m and 3m plus 3 together were excluded. So anytime you had consecutive multiples of 3, you have to exclude that partition. And so consequently, the 6 plus 3 here is to be thrown out. And Schur was subsequently able to I don't quite know where the red line came from. Anyway, this was able to show that if you make this exclusion, then this partition theorem is true. And this has led to an absolute explosion of theorems of this nature, so that many of the formulas in the Lost Notebook and many related formulas have been discovered in the intervening 100 years, and all lay their discovery, the direction of this research to the Rogers-Ramanujan identities. And while Rogers, in some sense, must be given credit for discovering the original formulas, the exploitation of these formulas by Ramanujan in the Lost Notebook, and indeed in his published papers before he wrote the Lost Notebook, is extensive, so that his contribution to this subject is absolutely massive. So this is a picture of Schur, and Schur was now in uncharted world. Nothing from either Euler's, Rogers, Ramanujan was helpful. So Schur examined the relevant finite generating functions. And so how would his proof go? So this is a 21st century version of what Schur effectively did. He's now going to say, well, I'm not going to look at all of the partitions. I'm going to restrict by the largest part. So d sub n of q is going to be the generating function for the partitions with largest part n. So that, for example, in the case of when D3, what partitions will be involved? Well, there will be q to the first power because there's one partition at q to the second power because there's one partition at 2, and q to the third power because there's one partition at 3. And so here you see these first 3 generating functions. And this fifth line, dn of q equals dn minus 1, plus q to the n times d n minus 3 chi of n q. This is quite clear if you just think about what's going on. I'm going to look at the partitions generated by dn according to whether or not n appears as a part or not. If n doesn't appear as a part, those are all covered by dn minus 1. If n appears as a part, the next largest part has to be at least 3 lower and 4 lower if n is a multiple of 3. And that's the effect of chi of n, is to make the next part 4 lower if n is a multiple of 3. Schur's proof essentially required that he prove the formula that you see here at the top of the screen. How does this work? Well, basically what you need to do is to find the defining recurrence for the d sub n's. And that would be a long and somewhat a boring process that I'm not going to take you through. But each side of this, you have to prove that it satisfies the same linear recurrence. And once you've done that, if they satisfy the same recurrence and satisfy the same initial conditions, then the theorem follows. And that is what Schur did. And the capital P that you see here is this finite product. And so, and n over j is what's called the Gaussian polynomial. The point about how this proves Schur's theorem has to do with taking the limit as n tends to infinity. As n tends to infinity, all the terms on the right-hand side vanish except the first term, because there's this q to the 3nj. And if j is not 0, this makes sure that the lowest term that you will see, because both p and the Gaussian polynomial are polynomials in q, so the lowest power will be q to the 3nj. And the only one such power that doesn't take q to that power to 0 as n tends to infinity is j equals 0. And so d in the limit d infinity of q is p infinity. Schur's proof is truly ingenious, especially since there were no guiding prototypes. In other words, he had the perseverance to see how the theorem went, but there was nothing to guide him in terms of what might be true, unlike what had already been done with regard to the Rogers-Ramanujan identities. As I mentioned earlier, the thing that we have going for us that even Schur in 1926 did not have going for him is that we can produce as many of these polynomials as we want, and we can factor them, we can expand them, we can do all sorts of things. And the interesting thing is that if you see this PN product here, well, I'll say a little more about this, but the point is that every sixth one of these, starting with D5, D11, D17, D23, fact is infinitely far from irreducible. It factors into products where you see more and more factors of this form. How does this then relate? And so what has been proved now in the 21st century is that this factorization continues on to infinity, so that you don't need a formula like you see at the top of the screen. You actually have the Schur polynomials themselves factoring in this beautiful manner. And if the trend continues, which has been proved that it does, the limit as n tends to infinity will be equal to this product as it increases in size. And you see that at each term, you get one more factor, and that has been proved. So in the first instance, the product's equal to this. But now you just use a little algebra to get this into a different form. And now you see that of the odd numbers, the numbers congruent to 3 mod 6 are canceled out in the denominator, and you're left with this product of 1 over 1 minus q to the 6n minus 1 minus q to the 1 minus q to the 6n minus 5. And that is precisely what one hoped would be true. One parts congruent to 1 or 5 mod 6. Here they are in this last line. And so you have a proof of Schur's theorem developed from just the intrinsic nature of these polynomials. So what you have is this marvelous progression. The results that you see on this screen this factorization was proved almost 100 years after Ramanujan and 90 years after Schur's original discovery, so that you see that Ramanujan's mathematics is alive and well. And while most of us are not as smart as Ramanujan, as I say, we have powerful tools to determine facts and theorems about mathematics that owes its origin to Ramanujan, and much of it to work that was done in the Lost Notebook. To prove that trend, he could have found a complete factorization by using the Q multi-sum package from RISC. So I want to pay tribute to my collaborators, Peter Pella and Axel Riese, who Axel has in particular developed this package that allows you to prove this sort of factorization that is actually going on here. It's an amazing thing. And with that, I want to leave time for questions or comments. So I thank you for your attention. It has been a great honor to participate in this conference, and I thank you from the bottom of my heart. Good.
Thank you very much, Professor Andrews, for a very nice talk. Are there any questions? So I had one question, Professor Andrews.
Good.
It is often said that there are no really easy proofs of the Rogers-Ramanujan identities. And I had read David Brasu's proof, and in this book by Borwein brothers, it was said that this proof comes closest to be the easiest one. Is it really true that, I mean, which proof would you consider as the easiest?
So the truth is that once you write down the right thing, then the proof's easy. But writing down the right thing is incredibly difficult. And it's the same is true of Brasu's proof. If you didn't have in mind the mechanism that has been now called the method of Bailey pairs and Bailey chains, if you didn't have that mechanism in mind, then it's hopeless. And what I would say is that the only really, really powerful mathematicians like Ramanujan and like Rogers were able to find proofs independently of these things. Schur also found a proof independently. But people like Hardy and Littlewood and Perron, all of whom are, and McMahon, all of whom were really outstanding mathematicians, they couldn't come up with it. So that when one does give Brasu's proof, or in fact, several other proofs, it is easy. But what is not easy is writing down the first thing that you need to do in order to prove this result. And much of that is true of everything in the Lost Notebook. There are some theorems, some identities in the Lost Notebook that are just really, really, really hard to come up with a proof, even after all the experience of the last 100 years. It's still very difficult. There are other things like the Rogers-Ramanujan identities that we are so used to and that we have seen so many proofs of. We think, well, that really isn't that hard. But you have, in order to really measure its difficulty, you have to go back to Hardy seeing it for the first time. Hardy being one of the foremost mathematical analysts of the 20th century, and didn't have a clue how to prove it. And I think that is more indicative of whether or not there is a simple proof. I do not think any proof really merits the name simple, although some are elegant. And once you start through it, then it's amazing how it falls together. But that's different from being really easy.
Okay, thank you. Yeah.
You bet.
So, any other questions? Okay, if not, I'll request people to maybe unmute and clap Professor Andrews for this beautiful talk.
Thank you.
Ranganath, when do we begin?
Sir is already joined. Professor Bruce Berndt already joined, sir.
Yeah, Professor Berndt has joined.
Sir, and there is a one question in the chat box. Sir, there is a one question in the chat box. Can I interpret this type of mathematics in the real world problem?
Andrews, I think there is this. Can I interpret this type of mathematics in the real world problem? I guess we can begin. Okay, so welcome again. We will begin with the next talk in this session. It will be delivered by Professor Bruce Berndt, who is Professor Emeritus of Mathematics at University of Illinois at Urbana-Champaign. Professor Berndt is also one of the world's foremost authorities on Ramanujan and his work. He has written 5 volumes on Ramanujan's notebook, another 5 volumes along with Professor George Andrews on Ramanujan's lost notebook. And today he will be Ramanujan. Before we ask Professor Berndt to start his talk, may I request everyone in the audience to please mute yourself? Okay, over to you, Professor Berndt.
Okay, good morning or good evening. So, one question. Yeah, I'm ready to begin if you wish. How long should I talk? I could talk, of course, for days about Ramanujan and his work.
Ranganath, I think it was an hour-long talk. So.
Yes, sir. Now 1 hour, na?
1 hour, yeah.
1 hour, okay. Yeah. Okay, should I begin then?
Sure.
Yeah.
Okay. Can you do full screen if possible?
Okay. Do I have a full screen here?
I don't think so, but if you could make it full screen.
So on my computer, I do have full screen.
Okay, so yeah, if it is full screen, yeah, Professor, sorry, we can begin.
Says you are screen sharing.
Yeah, I guess we can go ahead. Yeah.
Can you see the screen?
Yeah, we do see the screen. Yes.
Oh, okay. Okay. Yeah, I thought you couldn't see the screen. Okay. Well, thank you very much for the invitation to give this talk. I should remark, as you can see at the bottom of the slide, that I received another invitation to give a talk at this time, and so I asked the representative from Sri Sarada College for Women if I could double here at my talk and have then two invitations, one talk with two invitations. So let me give an outline of the lecture. So I'll begin by telling you something about Ramanujan's life. So I will repeat some of the things that George Andrews gave in his previous lecture. I'll talk about the history of Ramanujan's notebooks, and I'll say in a few minutes how I became interested in Ramanujan and his notebooks. I'll give some examples from his notebooks, and then talk about the lost notebook and give some history behind it. And of course, I will repeat then some of the things that George mentioned in his previous talk. And then I'll give some examples from Ramanujan's lost notebook, again, continuing the theme from George's previous talk. Okay, so a brief account of Ramanujan's life. So there are 4 photographs of Ramanujan that exist, and this is the most famous photograph. It's his passport photo. So in 1919, when he was preparing for his return to India, he had to have a passport photo. The photographer had to come to the nursing home to take his picture because Ramanujan was too sick to actually go to the photographer's studio to get his picture taken. So here is the famous picture. In the book Ramanujan by Hardy, the stamps of on the passport have been eliminated, but I prefer the original version of the photograph. So this is another picture of Ramanujan. Here you can see that he has a much fuller countenance. It was taken then a few years before the passport photo was taken, and it evidently was taken at the same setting as this photograph. So there is some controversy about when this photograph was taken. We think it was taken in 1916 while he was in England, but there are some people, and I feel their arguments are very good, that this was actually taken before Ramanujan left for England. So let me just briefly describe who was in this photograph. So this is Kayananda Rao. He was a student of Hardy, and he was in England at just about the same period, 5-year period that Ramanujan was in England. So this person here is Sattler Sundara Suryanarayana Shastri. He was actually a student at Oxford and became a very famous philosopher at the University of Madras. And then the fellow standing next to him, I always have to stop and make sure I pronounce his name correctly, is Taneti Suryanarayana. He also was a mathematics student at Cambridge and returned to India and was a very well-known teacher for many years. And this fellow is T. Adinaranda Chetty. He was not a scholar or a mathematician. He was very active in the independence movement. And by coincidence, he was actually born in Kumbakonam, where Ramanujan lived for most of his life. So those are 3 of the photographs that we have, and I'll give the 4th photograph later. So several years ago, I had the opportunity of actually visiting Ramanujan's original home. So Ramanujan was born in Erode on December 22nd, 1887. And after a few months, his mother returned to Kumbakonam with her son. And this is where Ramanujan actually lived for some years. There was no indication that this was the home of Ramanujan, except that the family living in the home had taken a picture of Ramanujan from a newspaper and cut it out and taped it to the entrance of the house. So this is behind then in the porch area behind the bamboo curtain that you saw in the previous photograph. Yeah. So Ramanujan, as a schoolboy, worked on a slate, as all children did in those days. This is actually the slate on which Ramanujan worked. It is in the family of S. Narayana Iyer, and in a few minutes I'll explain who S. Narayana Iyer is and how this slate of Ramanujan was fortunately preserved and is in their family. So, as I indicated, Ramanujan, as a schoolboy, did all of his work on a slate, including his mathematics, and he would record his results in notebooks, not with any proofs, but just the final results in notebooks. We don't know exactly when he began to record his results in notebooks. We do know, at least from the stories that have been handed down to us, that at the age of 12, he borrowed Loney's plane trigonometry from an older student and mastered this book. The title plane trigonometry is a little bit deceiving because there is much more in the book than trigonometry. For example, there are sections involving calculus. And then in 1915, he borrowed from the local government college library Carr's Synopsis in Pure and Applied Mathematics, which contains a little over 4,000 theorems, hardly with any proofs at all. So we think this is the background in which Ramanujan had as he entered the government college of Kumbakonam at the age of 16. Here is my favorite picture of myself holding Ramanujan's slate. My wife disagrees. She feels our wedding picture is my best picture. But anyway, let's just say now that this is one of my two best pictures that I have of myself. Well, let's talk a little bit about why Ramanujan never recorded any proofs in his notebooks. Well, as I indicated, perhaps he was greatly influenced by Carr's book, where there are hardly any proofs at all, just one result after another. So paper was expensive in those days. So working from his slate, as other students did at that time, he really couldn't afford to record his results he could only afford to record his results and not their proofs on paper. And furthermore, since his theorems were only a personal account of his discoveries, I'm sure Ramanujan felt there was really no need to record the proofs. He wasn't, he didn't have any idea about publishing his results. So just to remind him, later that, or to show others, there really wasn't any reason why he should record the proofs. And some people feel that he did not have proofs and he derived his results from religious inspiration. So I'd like to emphasize that he had proofs like any other mathematician. It's just that in many cases they weren't rigorous by then contemporary standards. And from time to time, mathematicians are asked, how do you prove certain results? Well, if the person asking the question is not a mathematician, you might say you got inspiration or you got some religious inspiration. So this is only natural. So I think that the reason that I favor most is really the third. In other words, he was just, recording a personal account of his discoveries, and he really didn't feel that he needed to give the proofs. If someone asked him about a proof, he would be able to produce it. Well, Ramanujan did not pass his exams after 1 year at the government college in Kumbakonam. After marrying in 1909, he moved to Madras in 1910. And for 15 months, he was supported there by R. Ramachandra Rao. So here is a photograph of the members of the Indian Mathematical Society in 1919. And there are certain people in this photograph, in fact, most of them, for which we have no other photograph. In particular, R. Ramachandra Rao is this person here in this photograph. And this person here in the front row is P.V. Seshu Iyer, who was Ramanujan's teacher, mathematics teacher, in the 1 year that Ramanujan was a student at the government college of Kumbakonam. So Ramanujan felt eventually that he really should have some sort of job and really not just, have a handout from R. Ramachandra Rao, who was fairly wealthy. He was a tax collector in Madras, or in a town nearby Madras. So in 1912, he made an application to the Madras Port Trust office to be a clerk there. And the head of the accounts department there was S. Narayana Iyer, who is actually in this photograph as well. He is this person here. So S. Narayana Iyer was actually a very well-known mathematician, and he was probably one of the best mathematicians in India at that time, but not working as a professional mathematician. As I indicated, he was head of the accounts department at the Madras Port Trust office. Well, he strongly urged Ramanujan to write English mathematicians about his work. He wrote M.J.M. Hill at the University of London. Hill didn't really understand Ramanujan's mathematics. He did reply, but he didn't really have a favorable impression of his work. Ramanujan also wrote two English mathematicians, Baker and Hobson, and as far as we know, they never replied. And then he wrote G.H. Hardy, and in this letter, he gave Hardy over 60 results. And Hardy was, as George Andrews mentioned in his previous talk, very impressed with Ramanujan's work, encouraged him to come to England so that his talents could be further developed. Because of family objections, Ramanujan was reluctant to go to England. Ramanujan wrote Hardy again with another 60 theorems, and Hardy returned. In his reply, he again urged Ramanujan to come to England. So finally, in March of 1914, after overcoming family disagreements about whether he should come to England or not, he made the journey to Cambridge. So at the time of his departure, he and S. Narayana Iyer exchanged slates. So I am told that at this time, at any rate, if you exchange slates with someone, this is a sign of deep respect that each has for the other. And indeed, Ramanujan was very thankful for Narayana Iyer, first of all, to hire him at the Madras Port Trust, and then actually encourage him to further his education at Cambridge. So here's a photograph of Hardy in Littlewood, this longtime collaborator. So let me just give you a couple of results from Ramanujan's first letter to Hardy. So he said 1, 2, 4, 5, 8, 9, etc. are numbers which are themselves squares or which can be expressed as a sum of two squares. And then he said the number of such numbers greater than a and less than x is equal to this integral plus a remainder. And he says theta of x is very small when compared to the previous integral. K and theta of x have been exactly found, though complicated. So Ramanujan also considered this problem in his notebooks. In his notebooks, he actually gives the value of k, an exact value. And he discusses theta of x, but he was optimistic as to how small this actually is. So this is really a remarkable result. So let me just quote Hardy. He says the dominant term, kb log b to the minus a half, which you would get just by an integration by parts, in Ramanujan's notation was first obtained by Landau in 1908. Ramanujan had none of Landau's weapons at his command. It is sufficiently marvelous that he should have even dreamt of problems such as these, problems which it has taken the finest mathematicians in Europe 100 years to solve, and of which the solution is incomplete to the present day. So indeed, this really was a remarkable result because Ramanujan just made a sort of a huge leap going from what was known in India at that time to a very famous result. So again, most mathematics proceeds continuously. There are jumps by great mathematicians. This was a huge jump that Ramanujan made. Let me give you just one more example from the notebooks. It's in the notebooks, but from Ramanujan's first letter to Hardy. It's one of my favorite results. So Ramanujan defines an integral phi of n in this way. So here is the same integral, but with the cosine replaced by a sine. So Ramanujan has this expressed in terms of phi of n and then phi of pi squared over n. So this is very interesting because this is the kind of relation one finds in the theory of theta functions or modular forms more generally. That is an expression involving phi and the reciprocal, phi of n and the reciprocal of n. Then Ramanujan says it's a complicated function, and he gives several numerical values for phi. And if you notice these, there really isn't, if you look at these carefully, you really can't find any pattern. Some of them involve pi, but others do not involve pi. They all involve algebraic numbers of some type. So as far as I know, there really has never been given, a formula which would encapsulate all of these results. So it's a very mysterious result, and it really deserves further study. So Ramanujan actually wrote a paper in which this result appears. So again, Ramanujan arrived in England in April of 1914, and already he was not feeling well. So here is just one sentence from a letter that he wrote to a friend in Madras on March 24th, 1915, a year later. I was not well till the beginning of this term owing to the weather, and consequently, I couldn't publish anything for about 5 months. In the following year, he obtained a degree from Cambridge, and he wrote a thesis on highly composite numbers. Unfortunately, the thesis no longer exists, at least it can't be found. However, almost all of the thesis, if not all of it, can be found in a very famous paper that he published called Highly Composite Numbers. Okay, so here is just one sentence from a letter that Hardy wrote to Mittag Leffler, a Swedish mathematician, on August 20th, 1917. You'll be sorry to hear that Mr. Ramanujan is seriously ill and that we are very much alarmed about him. He became a little bit better. His health improved a bit when he was elected as a Fellow of the Royal Society in February of 1918. So I've indicated the mathematicians who signed the document electing Ramanujan to the Royal Society. And some of them appear in italics. They were not at the meeting in which he was elected, but had evidently sent their ballots indicating their approval. That is Whittaker, Forsyth, and the famous philosopher and mathematician Alfred North Whitehead. But note, here we have Hobson and Baker. These are the two mathematicians that Ramanujan wrote before he wrote Hardy. So evidently they have changed their minds about how valuable Ramanujan's work really was. So here is a quote from another letter of Hardy to Francis Dewsbury, the Register at the University of Madras. And I'll quote from him later. There is at last, I am profoundly glad to say, a quite definite change for the better. I think we may now hope that he has turned the corner and he is on the road to a real recovery. His temperature has ceased to be irregular and he has gained nearly a stone in weight. The consensus of medical opinion is that he has been suffering from some obscure and only partially diagnosed source of blood poisoning, which is now dried up. Actually, the most common diagnosis that was made at that time, and which was also made after Ramanujan returned to India, is that he had tuberculosis. So many years later, a British physician examined all the records that could be found about Ramanujan's illness and concluded that Ramanujan died of hepatic amoebiasis. This is an amoebic infection of the liver area if dysentery is not treated properly. And he felt that Ramanujan had 2 incidences of dysentery before he actually went to England. He emphasized that dysentery was very common and could be treated if it was diagnosed, but if not diagnosed, it could get worse and kill you. So we don't really know what Ramanujan had, but tuberculosis and the diagnosis that was made by this English physician probably are the 2 main diagnoses, and one of them is probably correct. After Ramanujan returned to India in 1919, as George Andrews indicated, he wrote only 1 letter to Hardy before he died on April the 26th, 1920. And in this letter, he talked about his famous Mach theta functions. So after Ramanujan died, the plan was to publish Ramanujan's published papers, bring them together, and also publish his notebooks. In 1927, when Ramanujan's papers were collected for publication, however, there were not any pages from the notebooks or any edition of the notebooks were published at that time. So you see the editors are Hardy, P.V. Seshu Iyer, Ramanujan's teacher in his 1 year at the Government College of Kumbakonam, and B.M. Wilson, whom I'll talk about in just a few moments. If you look at this title page, you'll see that there's a very unusual aspect about it. So let me just pause for a few seconds if you can see something unusual about this title page. Well, note, B.M. Wilson's name is in larger letters than that of Hardy and P.V. Seshu Iyer. And I think the reason for this, again, very unusual to have something like this, is that Wilson really was the person who brought together all of the papers and put them in a form for publication. So that's just a brief account of Ramanujan's life. So now let me give you brief history of the notebooks. So I indicated we think that Ramanujan started to write the notebooks about the time that he entered the Government College of Kumbakonam, but we really do not have any kind of precise date. So let me quote from another letter that Ramanujan wrote after he arrived in England. I am doing my work very slowly. My notebook is sleeping in a corner for these 4 or 5 months. I am publishing only my present researches as I have not proved the results in my notebook rigorously. So I want to emphasize 2 things here. At this point, Ramanujan evidently just had one notebook, and that he really wasn't contributing anything to the notebooks. He was, as he said, it's just sleeping in a corner. So we think that really all the results in the notebooks then were proved while he was, or most of them were proved while he was in India. So in other words, over about a 10-year period from 1904 to 1914 when he left for England. So he really had more than one notebook, and he left this first notebook with Hardy upon returning to India. And he composed another notebook, evidently before he returned. So the notebook is a revised, enlarged edition of the first notebook. And he, as I said, evidently felt that, well, he had now a more fuller understanding of what he had done. And so, in fact, he added a lot to what he had in the first notebook. And then there is actually a short third notebook. We think that third notebook, which is just 33 pages, probably arose after he returned to India. So let me quote from a letter from Francis Dewsbury, whom I mentioned earlier, to Hardy. I have now seen your letter dated 19th November 1921 to Mr. Kayananda Rao. So remember, he was also a student of Hardy, and he appeared in the picture I gave you, in which you state that you have one of the late Mr. S. Ramanujan's notebooks with you. I shall be glad if you will return the original notebook when you have extracted from it the selected matter for printing in the memorial volume. So the memorial volume, as I indicated, really turned out to be only the published papers of Ramanujan. So Dewsbury thought that Hardy had a second notebook. In fact, he really had the first notebook of Ramanujan. So at that time, or shortly thereafter, a handwritten copy of the notebooks was made at the University of Madras and sent to Hardy. So Hardy indeed did return the first notebook to the University of Madras, and I think it was in 1925, a handwritten copy of these notebooks was sent to Hardy. And then shortly after the publication of the published papers, B.M. Wilson, who was one of the editors of the collected papers, and G.N. Watson agreed to start editing the notebooks. So by editing, what they meant was that if a result is new, then they should try to prove the result in the notebook. So this is Watson. So Wilson worked on this project for over 5 years, but then he unfortunately died from an infection that he had incurred in a hospital. And then Watson worked on this for over 10 years, but his interest evidently waned, and so the editing of the notebooks was never completed. The notebooks are actually at the University of Madras, and this is a photograph I took some years ago. So this is the first, second, and the third notebooks in the order. So let me just say a few more words about the pages in the notebooks. The second notebook, as I indicated, is the most important. It has 21 chapters of organized material, totaling 254 pages. And then there follows 100 pages of unorganized material. The third notebook has just 33 pages of unorganized material. There are 16 chapters, as I recall, in the first notebook, and then a lot of unorganized material. Here is a photograph I took of a couple pages in the notebooks. So note there is a reflection here. So let me just indicate in the olden days when I took this picture, we didn't have cameras on our cell phones or anything like this. I had a camera with a flash bulb on it, and the flash then reflected off of this page. Well, then you might ask, why would you have a reflection off of a page? Well, at the University of Madras, evidently these notebooks were not kept in a secure environment, that is a environment where the temperature and humidity were controlled. And the pages started to become deteriorated. And so then a lamination was made of the pages to ensure that no further destruction would take place. So that is why we have a reflection here, because of the lamination of the pages in the notebooks. The notebooks were not published actually until 1957, when the Tata Institute of Fundamental Research in Bombay published an edition. So this is a photograph I made of my copy of the notebooks. So in the first volume appear the first notebook, and the second volume has the second and third notebooks in it. In 2012, another edition was published, and this one is much clearer than the first edition, but I emphasize that almost everything in the first edition is recognizable. There are only a few places where it's difficult to read Ramanujan's writing. So that's a brief history of Ramanujan's notebooks up through the recent publication, the second edition. So if you'll permit me, I'll just say a few words about my interest in Ramanujan's notebooks and how I arrived at this point. So I was a graduate student at the University of Wisconsin, and in the spring semester of my third year, I took a course in modular forms from Rod Smart. So this was the first course in number theory that I ever had. And I enjoyed the course so much that I asked Smart to be my thesis advisor. And then in the following semester, the fall semester of my fourth year, I took a course from Marvin Knopp, and this was on modular forms with applications to number theory. And here is where I learned about Ramanujan for the first time. We learned about the congruences of the partition function in the course, and also about the famous Hardy-Ramanujan circle method. So I had never heard of Ramanujan until I took this course. Another professor at the University of Wisconsin who took a strong interest in my work, but unfortunately from whom I never had a course, was Richard Askey. This picture was actually taken in India. So Askey was very influential in my life for over 50 years. He died 2 years ago, this past fall. And I owe a lot to his guidance. So after I got my PhD, I went to the University of Glasgow for 1 year, and my mentor there was Robert Rankin. So Rankin was actually Hardy's last PhD student. And here, from Rankin, I learned about the notebooks for the first time. I was in his office one day, and we started talking about Ramanujan. And he said, I have a copy of the notebooks that the Tata Institute had published, and I'll be glad to loan you my copy of the notebooks. But at that time, I was not very wise at all. I told him I wasn't interested in his offer at all. Well, a huge mistake that I made, one of the worst mistakes I ever made in my life, I guess. Well, while I was at the University of Glasgow, I got an offer from the University of Illinois from Paul Bateman, who was actually the thesis advisor of Marvin Knopp, from whom I first learned about Ramanujan. So I accepted his offer. And in my second or third year at Illinois, he asked me to referee for him 2 papers of Emil Grosswald. So he had received them to referee, but he didn't have time, and so he asked me to referee the papers. So as you can see, Grosswald had proved some results from Ramanujan's notebooks. So as you can see, I recommended acceptance of the papers. So here's a photograph of Grosswald. I'll just tell you about one result that Grosswald proved. If alpha and beta are positive integers such that alpha beta is pi squared and n is a positive integer, we have this relation involving the Riemann zeta function. So I didn't put down the definition here, but zeta of n is the sum over 1 over n to the z, n running from 1 to infinity, and the real part of z positive, greater than 1. So this is very interesting. We don't know arithmetically very little about zeta of 2n plus 1. So here's this beautiful symmetric relation between the zeta function in these series. The b2k, b2n plus 2 minus k, 2k are the Bernoulli numbers. So let me emphasize that Ramanujan loves symmetry, and if he could state a result in a symmetric form, he would. So this kind of symmetry in the hypothesis is very familiar. When you read about Ramanujan's work, again, there are a number of results which are put by him, if they could be, in the symmetric notation. So let me say just a few more words about this formula, which has become very famous. If you let alpha and beta be pi, and then replace n by 2n plus 1, you get this formula for zeta 4n plus 3. So this particular case was actually found by the Czech mathematician Lerch in 1901. So this is really a remarkable identity. It shows that zeta 4n plus 3 is a rational multiple of pi to the 4n plus 3, but there's, so to speak, you might say an error term being, and I'm being very facetious here, a rapidly convergent series. So zeta of 2n is a rational multiple of pi to the 2n. It's that kind of formula does not hold for zeta at odd values, but here we see that zeta 4n plus 3 is almost a rational multiple of pi to the 4n plus 3. So of course I'm speaking, very, imprecisely here. And these formulas are in chapter 14 of Ramanujan's second notebook. And here is the page where these formulas are actually found. So let me just get back to my history a little bit here. I've spent my first sabbatical at the Institute for Advanced Study in Princeton. And one day in February 1974, I realized all of a sudden that these results that Grosswald had proved, I could now prove using some work I was doing on transformation formulas for Eisenstein series. So this was just a very exciting for me to actually prove some formulas from Ramanujan's notebooks. So I immediately went to the Princeton Library and checked out the notebooks. Again, this is the edition that was in the library, and I found a few more formulas I could prove, but a few thousand others that I had no idea how to prove. So I didn't do too much, except try to get as much out of my methods as I could. But then in the spring of 1976, I decided, well, let's try to prove everything in chapter 14 of Ramanujan's second notebook. So I just took this as a personal challenge to see what I could do. I, of course, chose this chapter because I already had a head start. I had proven some of these formulas in chapter 14 because they were in Grosswald's papers. So I worked on this for over a year. There were 87 results altogether in the chapter. And then George Andrews visited Illinois. He told me, so this was 2 years after he found the lost notebook. He said that when he visited the library at Trinity College, Cambridge, and found the lost notebook, he also saw that the efforts that Watson and Wilson had made to edit the notebooks had been preserved there. So I thought, well, if I had a copy of their notes, then maybe I could edit further chapters. So very kindly, the librarian at the Cambridge University made a Xerox copy of the notebooks, or the notes that Watson and Wilson had accumulated. And so then I went back to the start of the second notebook and then just gradually worked my way through over the years. And after a little over 20 years of work, I finally completed the task. I would like to emphasize I had an enormous amount of help. In particular, I had several PhD students, and they helped in proving several formulas from the notebooks. So let me next just say a few words about some of the topics in Ramanujan's notebooks. So there are a lot of results on Q series. In George Andrews' lecture, it was full of Q series. It was almost entirely on Q series. So I'll use this Q product notation, which Ramanujan did not use. So in other words, 1 minus AQ up to 1 minus AQ to the n minus 1. And this is the infinite version when you let n tend to infinity. So this is called the base, this Q. So if the base Q is constant, it doesn't change in an analysis when we leave off the notation. But as I indicated, Ramanujan actually didn't use this notation. If there was one topic which you would say is more prominent than any other topic in the notebooks, it would be theta functions. So here is Ramanujan's definition of a general theta function. And this identity is called the Jacobi triple product identity. Well, note the symmetry in this definition of f of AB. Normally, when one discusses theta functions, the definition given of a general theta function is not in this symmetric notation. So this notation, as far as I know, was first used by Ramanujan. And for his purposes, this is the best notation, this symmetric definition. You know, for other purposes, other studies involving theta functions, maybe the classical notation is best. And these are the three most important cases when A and B are both Q. So then we have the squares. When we have Q and Q cubed. So I folded up the terms with negative index, just replace n by minus n. So this gives the representation for psi of Q, or f of Q, Q cubed. And then f of minus Q, which George also mentioned in his talk, is just Q, Q sub infinity. And these are the pentagonal numbers. So I emphasize that Ramanujan didn't use this classical notation. He didn't use any of the standard notation for theta functions. The elliptic functions are closely allied with theta functions, and Ramanujan had a number of results on elliptic functions, but did not use any of the standard notation. No. Now let me briefly indicate something which is a little more advanced, but I want to make a certain point about this topic. So this is the complete elliptic integral of the first kind. If you take the integrand and expand it in a geometric series, you'll get this series, and I'm here now using the rising factorial notation, or the shifted factorial notation. And this is a hypergeometric function. So this is not, I really won't use this, but to just give this as a point of information, you can write this as a hypergeometric function. So k is called the modulus, and square root of 1 minus k squared is called the complementary modulus. Okay, so this definition might seem, out of the blue to you, but it is natural in the theory of theta functions and elliptic functions. So here, k, k prime, l, and l prime, they're complete elliptic integrals of the first kind, and they're associated with these moduli, k, k prime, l, and l prime. And suppose you have a relation of this type amongst all the four complete elliptic integrals, and here n is some positive integer. And then a modular equation of degree n is a relation between k and l, which is induced by this relation. So Ramanujan actually sets alpha to be k squared and beta to be l squared. So you can write this definition in terms of hypergeometric functions, as I indicated on the previous slide. This is actually how Ramanujan thought of it. Well, here are so 3 examples of modular equations that Ramanujan found. He loved this topic. In his notebooks, he has nearly 200 modular equations. And for certain degrees, for certain small prime degrees, he has lots of them. So in particular for degree 3, as I recall, he had around 14 different equations. So note the symmetry in these modular equations. Again, Ramanujan loved symmetry. He was evidently fascinated with these equations involving the moduli alpha and beta. So one interesting thing about these equations is that if you have a prime degree, the equations never repeat. So in other words, here we have really 2 modular equations of degree 3. You will never find these equations for any other degree. So in other words, they are unique for the given degree. So and that's true for every prime p. Here is a very unusual result. It's actually in Ramanujan's second letter to Hardy, and it's in the notebooks. So this really is a theta function here. So he writes this as a continued fraction, a very simple, beautiful continued fraction. Okay, they're not exactly equal, but you have some terms which make them equal, but they're really an infinite number of terms here, so to speak. This series does not converge. But Ramanujan noticed that. He just stopped at this number of terms, and he used the word nearly. Yeah. Okay, so in other words, what he's saying is that this theta function is this continued fraction plus this polynomial in x squared and x nearly. Ramanujan often used the expression nearly and very nearly to indicate that he didn't have an exact formula, but it was almost an exact formula. This is really what's called an asymptotic expansion. Okay, I think I'll skip this just as a matter of time. Okay, so sorry. For some reason here, I've lost all of my. There is a mistake in my compilation. So if you'll excuse me, I don't know what happened. I have to go. all of a sudden my my PDF file went to the end of the file. Okay. Sorry here, I'll have to go back. Yeah. Okay. So, sorry, I'm not sure what happened in the compilation of my PDF file here. So let me just then summarize. Here are some of the topics in the notebooks. There are a lot of identities involving infinite series. A lot of results on theta functions and elliptic functions. There's a whole chapter on hypergeometric series. A lot of results on Q series. Integrals, asymptotic expansions. I indicated just one of those. I indicated just one result on continued fractions. There are many results on continued fractions and in general number theory. Okay, so let me indicate now the history of Ramanujan's lost notebook. So I'll repeat some of the things that George gave. Let me just go to this photograph that George kindly sent to me. This was taken at Cambridge when Ramanujan's notebook was found by George. So these are his two daughters, Amy and Katie. Amy wrote a very nice children's book on Ramanujan, which was published about a year ago. I highly recommend it. And Lucy Slater, who did a lot of important work in hypergeometric series, encouraged George to go to Trinity College Library to examine the papers of the late G.N. Watson, and there's where George found the lost notebook. So I will skip this. So how did this manuscript reach Trinity College Library? Well, let me go back to Francis Dewsbury, whom I quoted earlier. So this is in a letter of August 30th, 1923 to Hardy. I have the honor to advise dispatch today to your address per registered and insured parcel post of the 4 manuscript notebooks referred to in my letter. And so here evidently the notebooks were divided into 4 parts during this shipment. I also forward a packet of miscellaneous papers which have not been copied. It is left to you to decide whether any or all of them should find a place in the proposed memorial volume. Kindly preserve them for ultimate return to this office. Evidently, Hardy never returned any of these papers. So unfortunately, Dewsbury and Hardy never, made a record of actually what was in this packet of papers, but almost certainly the packet of papers included Ramanujan's lost notebook. So sometime in the late 1930s, perhaps, Hardy took the lost notebook, and it wasn't called the lost notebook then, but this manuscript, and gave it to Watson. And Watson wrote several papers on the mock data functions, which were the dominant topic in the lost notebook. In particular, in his retiring address to the London Mathematical Society, he was president for some years. He wrote an account of the mock data functions, which he called the final problem. So he chose this title just because the mock data functions indeed were the last topic that Ramanujan discussed before he died. So he sort of borrowed this title from a famous book or story written by Sir Arthur Conan Doyle in his Adventures of Sherlock Holmes. And one more thing, Sherlock Holmes' sidekick in all these famous stories was Dr. Watson. Well, Watson died in 1965, and shortly thereafter, Robert Rankin paid a visit to Mrs. Watson. Rankine had actually succeeded Watson as the professor of mathematics at the University of Birmingham after Watson retired. But when a professorship opened at the University of Glasgow, Rankine, being a Scotsman, took that professorship. And that's, you'll recall, where I met Rankine on my 1 year that I spent at the University of Glasgow. Okay, so since George talked about topics in the Lost Notebook, I will skip some of the things that he mentioned and head to a couple other topics. So the Lost Notebook was actually not published until 1988. And with the publication, many other manuscripts of Ramanujan were also published. So evidently, these were also in this shipment that was made from Dewsbury to Hardy in 1923. So unfortunately, many of some of these manuscripts are now lost, but Watson made a copy of them. So here are 7 manuscripts in Watson's handwriting, but we actually do not have the originals that Ramanujan sent or were sent to Hardy. Yeah. So the most important ones are this one involving 40 identities involving the Rogers-Ramanujan functions, which George talked to you about, and this manuscript on P of n and tau of n being the famous Ramanujan tau function. Yeah. So, seeing these handwritten manuscripts of that Watson made, you sort of think about, well, were there other manuscripts that were lost? Because the originals for these have been lost. So it's, in other words, these manuscripts that were sent to Hardy and then Watson were not treated with the care in which they really should have been treated. Yeah. I'm going to tell you just about 1 or 2 results from the pages that were published with the Lost Notebook, that is in the 1988 edition. So we'll let R2 of n be the number of representations of the positive integer n as a sum of 2 squares. We count different signs in different orders as being distinct. So you can take 5, it's plus or minus 2 squared plus or minus 1 squared, but you can invert the summands. So R2 of 5 is 8. Yeah. Now you can take each of these representations as a sum of 2 squares and associate it with a lattice point in the plane. So for example, if you take 5 as minus 2 squared plus 1 squared, you associate that with minus 2, 1. And then each lattice point can be associated with a unit square. Of course, there are 4 possibilities for this square. So let's be consistent, and we will take the unit square for which the lattice point is in the southwest corner. Okay, so here are all the squares of representations of numbers in a circle of radius square root x. So in other words, remember by Pythagorean theorem, a squared plus b squared is equal to x squared. So in other words, the distance, we're just using Pythagorean theorem here. So if we want to know what's the sum of R2 of n over n less than or equal to x, the result, so the natural approximation would be the area of the circle. So let me just go back. This is not going to be an exact formula. So again, I colored red all the squares associated with lattice points inside the circle. Yeah. So it's an approximation, but not an exact formula. So there's going to be an error term, which we call P of x. And this prime on the summation sign indicates that we only count a half R2 of x if x is an integer. So this is the sum which naturally arises in the study here. So the order of this error term is not known. It's an unsolved problem. Gauss was the first person to examine this. He observed that the sum is less than x pi times square root of x plus square root of 2 squared. In other words, all those squares are in a circle with radius square root x plus square root 2. And then if you take a circle of radius square root x minus square root 2, it'll be entirely covered red. So from these two inequalities for the sum of r of x, you get that r of x is pi x plus some error term, which is big O of square root of x. So let me just explain that notation briefly. We say a function f of x is big O of g of x as x tends to infinity if there are constants c and x0 such that you have an inequality of this type for all x sufficiently large. So what's the order of this error term? We don't know. Hardy worked on this problem, and in a paper published shortly after Ramanujan arrived in England, Hardy got a very famous result on this, which I'll indicate in just a moment. So in this paper, Hardy gives this formula for the sum function. So the error term then is represented by an infinite series of Bessel functions. And Hardy says this in the paper, and I've always found this very unusual. He says the form of this equation was suggested to me by Mr. S. Ramanujan, to whom I had communicated the analogous result for d of 1 plus d of 2 up through d of n, where d of n is the number of divisors of n. So this seems a bit strange. In other words, if the form was suggested to him, you really had to have the formula himself. In other words, Ramanujan wouldn't say, "Oh, I think there's some formula for the error term in terms of Bessel functions." You wouldn't say this unless you really had the formula. Yeah. So using this formula, Sierpinski showed that the error term is big O of x to the 1/3, which is an improvement upon what Gauss said. And there have been many improvements since then using this identity, but we still don't know the exact form or the exact order of the term. So there's a result in Ramanujan's Lost Notebook, or in a manuscript published with the Lost Notebook, which addresses this problem. So let me first tell you about an identity of Jacobi. This is often proved in an elementary course in number theory. So if you take this identity and rewrite it in terms of a sine function, this is easy to see, and plug that in, this sum of R2 of n. Okay, so here I'm going to write n as d times j. So for any divisor d of n, you can do this. So we can sum then over all pairs dj where the product is less than or equal to x. I'm going to sum on j first now. And since the summands don't depend upon j, then the value of the sum is just square brackets of x over d, where this is the greatest integer function. Okay, so I'm going to leave this at this point, and I'll come back to this later. So this is a page published with Ramanujan's Lost Notebook. And this is the formula at the top of the page, the first of two formulas. Okay, so here we have a finite sum on the left, but a double sum on Bessel functions on the right-hand side. So this was first proved by my former student Sun Kim, my colleague Alexander Zaharescu, and I in 2013. So this is a picture of Zaharescu. This is a picture of Sun Kim. And here I'm saying that apparently this formula was proved by Zarescu and myself in 2006. So why am I saying this when I just said that the formula was just proved in 2013 by Sun, Alexander, and myself? Well, if you look carefully at the series, note here the sum begins with n, and then we go to m. But in the formula that Zarescu and I proved, we begin with m and then n. So I'd like to emphasize that the proof that we gave here, we could not use for Ramanujan's formulation. It didn't work at all. We would need entirely a new idea. So it took us then several years to get a new idea to prove the formula in which Ramanujan stated it. So this is a very interesting formula. So again, recall the formula of Ramanujan that Hardy gave in his paper. If you take theta to be a quarter in that formula, then the sum on the left side is exactly that sum of involving Jacobi's formula that I gave you a few minutes ago. So here is the big problem then, or the big question: can we use this extra parameter theta to attack the circle problem? So we think that Ramanujan derived this formula in order to attack the circle problem, but we have no idea what his thinking was, and we have not been able to actually use this formula. So let me just briefly mention another result, which is in the paper that Hardy wrote. So he gives this formula, just states this formula in the paper. It's a beautiful formula. So note that you get from the left side to the right side by interchanging the A and B. So beautiful result, again, indicating symmetry. It's not given anywhere in Ramanujan's work except in Hardy's paper. Well, if you differentiate this formula with respect to B, let A tend to 0, make a change of variable, write this in terms of S and use analytic continuation, you get this formula. Well, this is exactly the formula that Hardy used to prove that the error term in the circle problem is omega plus or minus x to the 1/4. So let me just briefly explain this notation. On the plus sign, this means that there's some sequence tending to infinity such that on the sequence, the error term is greater than a positive constant C1 times xn to the 1/4. So no matter what positive constant we choose, we can find some sequence, of course, depending upon this constant, such that this error term is this large. And we can do the same thing on the negative side. So in other words, what this theorem of Hardy says is that we cannot have an error term of big O of x to the 1/4 because this result that he proves contradicts that. We think this is the correct order after you would add an x to the epsilon for every epsilon greater than 0, but no one has ever proved this. Well, let me just indicate one more result before I end my talk. In that partial manuscript, there is another formula involving a sine replaced by a cosine, and instead of the formula involving R2 of n, it's a formula involving the divisor function d of n. And there's a very famous unsolved problem involving the sum of the divisor function d of n, n less than or equal to x. So we think Ramanujan derived this formula to attack the second unsolved problem. This formula was more difficult to prove, and it was proved by Junxian Li, a student of Zarescu and myself in 2019. And we chose this title for our paper, and we chose this journal because of Watson's paper that he wrote on the final problem, and he published in the Proceedings of the London. So the reason why we call this the final problem is that this was the last result in Ramanujan's lost notebook and other unpublished papers that was to be proved. We think that George and I approved all the other results in the publication of the lost notebook from 1988. So this is a photograph of Zarescu and Junqian Li. So let me just end by quoting Freeman Dyson, also prominent in George Andrews' talk. We had a conference at the University of Illinois in 1987 to commemorate the 100th anniversary of Ramanujan's birth. And in that lecture, Dyson said, "I am grateful to the organizers of this conference for bringing me here and giving me a chance to enjoy all the new flowers that have been growing in recent years in Ramanujan's garden." And then at the end of his lecture, he said, "Whenever I am angry or depressed, I pull down the collected papers from the shelf and take a quiet stroll in Ramanujan's garden. I recommend this therapy to all of you who suffer from headaches or jangled nerves. And Ramanujan's papers are not only good therapy for headaches, they also are full of beautiful ideas which may help you do more interesting mathematics." Well, to this quote, I would add Ramanujan's notebooks and Ramanujan's lost notebooks. So focus your mathematical interest on Ramanujan's mathematics. It will make you happy, and you will get rid of jangled nerves if you do. So thank you very much for the invitation.
Thank you, Professor Berndt, for a beautiful talk. Are there any questions? So I had one question about this double Bessel series identity that you had. You said that when we have the one for R2 of n, and if you take theta equal to 1/4, then this is what is giving the special case, right? Like the formula.
Right. Yeah.
For any other values of theta between 0 and 1, is it giving us some other arithmetic functions? Or
yes, you can actually express. So there's another famous problem. I mean, there are really many, but this is just one of several. If you take the number of representations of an integer n, let's say cap n, as a sum of mn in smaller, in other words, lowercase, mn plus m squared plus n squared. So finding the summatory function of this, again, you could get a main term and there'll be an error term. That is a famous unsolved problem, and you can actually get a formula for the summatory function for this quadratic form in terms of Bessel functions. So that's another special case. I think that's stated to be a sixth, if I recall. So,
okay.
So you can get a few other nice special cases from this formula. That's correct. Yeah.
Okay. Right. Thank you. Any other questions? Okay. If not, I'll again request audience to unmute and clap for Professor Berndt's beautiful talk.
Thank you very much.
I'd like to thank both Professor George Andrews and Professor Bruce Berndt for very informative and very nice talks. With this, we end this session for today. Tomorrow morning, I guess there are a few more talks. So I'll hand over now to Ranganath.
Yes, sir. Yes, sir. Yes. So thank you, sir. On behalf of Department of Mathematics, School of Physical Science, Central University of Karnataka, and the entire ICND 2021 team, I want to thank the Professor George E. Andrews and Professor Bruce C. Berndt for accepting our invitation and for today's talk. Thank you, sir. Thank you so much. And also I thank Professor Atul Dixit for chairing this session. And also I thank all the participants for listening patiently. So thank you. Good night, Punana.
Thank
And
you.
also good morning to Bruce Berndt, sir.
Thank you.
Thank you so much. Thank you so much.
Yes.